Okay, so hello everyone. I'm Maura Pintor and I'm a postdoctoral researcher at University of Cagliari. And I welcome you to a new event of our seminar series on machine learning security. So today's guest is Andrei Lapanik, and he will be introduced very soon. But right before we start, I want to share some information about the seminars. So first of all, the event is live streamed and recorded. So if you don't want to be recorded, feel free to join the YouTube stream. But for questions, we will give priority to the Zoom chat and Zoom call. So please, I'm going to ask who wants to ask questions to raise their hand and speak up, or just to type on the Zoom chat. And then if there is time left until the end of the event, we will answer YouTube questions. Then for knowing more about our events and being always updated, we have all the possible social channels that will be posted on the Zoom chat very soon. And you can follow us on Twitter, LinkedIn, or also Eventbrite for receiving the emails. And if you want to know more about machine learning security, we also have a course on the same channel where we are live streaming, and feel free to check it out. It will definitely contain relevant information on this topic. And lastly, I want to thank all people who helped me organize these seminars. And now let's give the stage to Ambra, who will introduce our speaker for today.
Good morning to everybody. Today, as Maura said, we will have Andrei Lapanik. He started his career working as a software engineer. And in its almost 20-year professional path, he managed to get an extensive experience also as a lead software engineer, project manager, freelancer, and distributed team manager, co-founder and product owner, vice-president of data science. Today he is truly passionate about recent artificial intelligence progress and potential which this technology has to transform our lives. Having a strong mathematical background, he started as a freelancer, data science, 5 years ago, and ended up merging his consulting company to a bigger player. Currently, he works at Intuition Machines as a machine learning engineer, and in particular, he is working at the product called captcha. So I leave the stage to Andrei, and thank you again to be here and to give this talk.
Thank you for such an extensive introduction. And let me share my screen. So let me start the presentation. Can you see my screen now?
Yes.
Yes, so I'm going to talk today about practical applications of adversarial machine learning. I know there are a lot of theoretical research, but in our company, we managed to use these for business. And I hope that it would be interesting for both practitioner and theoretical researchers, what kind of decision we make when we consider different kind of technologies. So in this talk, I have only a bit of theory, and I'm going to focus on the practical examples and decision behind them. Also, yes, as I mentioned, so how theoretical results are selected to be used in a customer-facing product. And I hope to hear not only questions, but also opinions, even strong opinions, any ideas, so feel free to share and interrupt me in any time. Yeah, a couple of words about myself. Currently, I'm an ML engineer in Intuition Machines. I have a computational physics background in fluid dynamics, but actually I'm more on the practical side. So last 20 years, I'm just doing software development and try to use my knowledge at best, creating products. And a couple of words about product and a company that I'm working in. So captcha is a major product in intuition machines. We are already quite big, so we have 1 million publisher, like we have 25 and more online properties protected, serving about 20% of internet, but don't ask me how it was calculated. And actually we serve 100 million image impressions per day. So I think from this perspective, my talk would be interesting, not only by like optimizing attacks, but also how to scale them. And so yeah, 10 language options and over 250 locations are covered around the globe. And I'd like to mention that like all further conclusions here are mine, and they may not represent essentially a company opinion. So let's talk about problem statement. What we do in captcha, we protect websites from bots. There are actually a lot of bots. So like simple examples are scrapers, spammers, spiders, and downloaders, e-commerce bots like sneaker bots, Grinch bots, ticket bots, and a lot more. What happens is like you have a website and there is some automation that tries to abuse the ability, for instance, to buy products or to download something, or they just scrape information. And like in a simple case, you get extra traffic that you don't want to get. In the more complicated scenarios, they can buy something and break the user experience to do like useful actions on your website. And if your website grows, it becomes like a big problem. Bots also evolve and become more and more complicated. They use computer vision, natural language understanding. Some captchas have this voice capability, and some bots try to understand, like to read this voice to solve challenges. And this is why we are like deeply involved in this topic also, and how to actually break bots to understand what we ask to do on the website, but keep human clear about the goal. And this is how we actually separate bots from humans. And I'm sure you're familiar what captcha is, and you can easily imagine like what kind of problems stand behind captcha systems. And here we comes to adversarial examples. I'm not going to go deeply into this topic because I hope that people who join this seminar are actually familiar with basic concepts. But what I'm trying to say here is this approach seems to be quite natural. So we want to fool bots that use computer vision system. So yeah, everybody knows about adversarial examples today at some level. And we also see this as a natural way actually to try to defeat bots. What's good about our product is that we can do A/B testing. Like we can verify, we have regular jobs that are kind of provided to bots, and bots try to solve it. And we have kind of modified jobs that can be compared. And if we see the difference between behavior and traffic patterns for these two types of jobs, we can say that yes, this approach that we use to fool bots actually works, because like there is a difference in traffic behavior, and it helps us to understand what really works on practice from those theoretical advances that we have today. And actually Google also does it. So you can see these screenshots that I took on my laptop. And this is the true Google CAPTCHA. It's not easy to get it. Actually, you have to be super suspicious to see this CAPTCHA with adversarial noise. But yes, Google also does it. And why not to do it on our side? Any questions so far?
I think we are good.
Okay, great. Let's continue. So, samples are actually publicly available on GitHub. So why not to do white box attacks? As you know, white box attacks is a type of attacks that you have access to a model, and you can actually calculate gradient, and using this gradient, you can modify input to get an adversarial example that is fool the model in a certain direction, untargeted or targeted. It is kind of a nice idea, but unfortunately, you have to keep in mind that when you do a white box attack, you deal with input tensor, not actually like an image is an image. So we have kind of an image of a panda, and if we, for instance, resize this image of a panda, this is still an image of a panda, but this is a different tensor. And here is the problem. We serve small images to be able to optimize our content delivery. And we actually don't know how our image is going to be resized. And from that perspective, it kind of shifts us to the direction of black box attacks. Also, I keep in mind this nice talk on your channel about kind of attacks of using image resizing. But in our case, we mostly deal with the situation when we have a small image and the potential bot would have to make it bigger to work with it. And so we can't hide any additional information in our images. And none of our white box attacks from that perspective were successful. Of course, you can introduce some additional layers, but at the end of the day, when you don't know exactly what is the size of your kind of final input tensor, I don't expect that any white box attack is going to be successful. This is the first thing. And the second thing is that actually transferability of white box attacks is still, I would say, questionable. And we want to cover kind of a lot in a one shot, because sometimes we can assume what kind of models bot uses, but most of the time we just don't know. So we are totally in the black box case. And here we go for black box attacks. Yeah, as I mentioned, we don't know most of attackers. So we need to assume that everything is possible. By everything, I mean like they would potentially use some obviously pre-trained model, like well-known ResNet, YOLO, Inception, whatever. Then they can use like special private models, ensembles. What they can do also, they can train our images, some subset of our images, and start training their own models on our images. Also, they can use like Cloud Vision API, whatever possible, AWS, Google, Azure, if they don't want to deal with infrastructure. This is our kind of environment that we are operating in. And at the same time, we can measure the impact of our black box attack. So how do we do it? We have like 2 image sets deployed at the same time. Maybe original or original plus noise if we do patches. Otherwise, we have like a reference job, which we know for sure what we can expect from different like activity patterns for that job. And in the same time, we can deploy adversarial set of images together with this job and compare what happens like in real time for both of those jobs. And we do it for the same limited site set. So we expect to get similar traffic and check the pass rate. So at least if pass rate drops for adversarial job, we know that it has some impact, and we are actually happy with it. Even if we, at the end of the day, if we don't understand what's still behind of those bots that try to work with patched images, but still, like, we are happy to see that there is a difference and we can analyze it further. Yeah, and before we jump into particular methods of doing black box attacks, do you have any questions about like maybe product or environment that we operate in? Maybe that I can clarify.
I have a quick question. So
Yeah.
usually adversarial examples are thought of being very small, imperceptible to the human eye. In this case, I think this is quite a relaxed constraint in the sense that it doesn't matter if the human sees a perturbation, but it matters that they can still recognize the image, right?
Not exactly. That's a good question, and I will talk about it a bit later. I think this is kind of a bottom line of the whole story.
Okay, then yeah. I'll wait for it.
Cool. So let's get into practice. As you may know, like if you do a black box attacks, just like in white box attacks, as a rule of thumb, if you get a gradient somehow, or you can estimate a gradient, like it's better than operate without gradient. So the first approach that I like from this perspective was using a natural evolution strategy, which actually just tried to estimate gradient like in a very simple way. So instead of gradient, the estimated expected value of gradient is used as presented in this formula. From the practical point of view, it means that like having evolution strategy means that you sample some kind of examples around the point of interest, and when you have these samples, just like in maybe Monte Carlo case, then after having all the, like after you calculate values for all of those samples, you try to estimate something. In this case, you can see that this is a simple formula, which is kind of a, like, you can imagine this is just a mean value of scores that you get from any model or API that you can put as a foundation of your gradient estimation. And it's really great because there is no restriction, like there are no assumptions about the function that you try to, that you kind of, for which you try to calculate this gradient. And this is really kind of a simple formula that you can use to generate adversarial perturbations. There are some kind of optimization behind it, and there are some magic numbers that are recommended, for instance, for search variance or for kind of your population. It is better to have a symmetrical population than a non-symmetrical population in this case. But you can kind of select a point which is your original example that you want to perturbate. Then you sample something around of this point, and after this, then you collect scores for this population, and then you try to kind of estimate the right gradient direction. If you have a targeted attack, then into the targeted direction, or if you have untargeted attack, then you try to estimate just something as far outside as possible for your point. And that's it. So you don't have to do anything else. And if you have a gradient, you just update your image and you get a result. For any theoretical background of this approach or more details, I encourage you to check related article. Also, it is better to do this type of perturbation on low frequency of kind of image information than like just do it for the whole image. If you want to optimize the amount of queries that you have to do to your model in order to calculate the scores that you will put like as a foundation of your gradient estimation. And this is actually a crucial thing for this approach. So you try to find the right gradient for your image. And in order to do this, you have to sample a lot of points to get a usable result. And let's take a look at some examples. So here are some examples for AWS, and I provided, when you get a gradient estimation, you multiply it for some, you multiply it to some budget to control the noise that you want to apply to your image. And here is the minimum budget I was able to calculate to the provided image to get a perception like how deep we can go with, like, obviously we want to produce as less noise as possible. As you, Maura, mentioned, like we actually have to do something imperceptible, but unfortunately this is quite tricky for black box attacks. And here are like several examples with related noise budget for images. My feeling about like the whole process was that the more information you get in your image that you want to change, actually the more noise you need to apply in order to break, for instance, AWS image recognition system. If you have like a lot of space, then you can, and less details, then you can get like a working image with less noise. But if you have like a lot of details, just like in those buses, and less background, you have to provide kind of more noise. And actually, if you want to make it more transferable, because all of those images are actually crafted for AWS, you have to go with even more noise. And this is how it really looks like. So before I would make any maybe live demo, do you have any questions about this approach or how we start working with black box attacks? Yeah.
I don't see questions, but I have one.
Okay. Yeah,
I wanted to know how costly is this process, because I can guess
So,
for estimating a gradient,
yeah,
this takes a long time.
You know this topic, so your questions like go a bit ahead of time. So everything will be covered quite lately. But let me do a small live demo. Do you see my browser?
Yes.
Yeah, so this is the demo page for Google Cloud Vision API. And the point with this NES attack is that basically you can craft adversarial examples at home. Let me change actually. So this is how it looks like. Yeah, and let's try it out. Let's put a plane for Google Cloud Vision, and let's check this out. What Google Cloud think about this image. Yeah, so basically, not exactly aircraft, so vehicle is the closest thing that we can consider, like, oh, there is an aircraft, but it's not a kind of top 10. You have to go deep into all the classes. And the other example could be, for instance, let's take a bus. Oh, no, it doesn't work like this. Sorry. So I have to request for a new file. Yeah. Let's do and let's go for the bus.
Okay, we see it
Yeah.
now.
So it's a paint and pattern and painting, and this is actually quite popular class when you, for instance, when you do untargeted attack for all those APIs. Obviously, I don't know what's the model behind it and how does it work, but you can actually break it, and it's not super problematic. Also, I have examples for AWS, but unfortunately, I have to log into AWS in order to use the recognition API. But let's take maybe some other bus that is crafted for AWS and see how it works.
So we are doing a transfer attack now.
No, it's not a transfer attack. This is how you check how things actually work. Like from
No, I mean,
perspective. When you,
I mean by uploading an image crafted with the AWS.
yes, and the fun thing, if you attack GCP, you can't fool AWS. But if you, for instance, attack AWS, you can fool GCP. And here is the trick that AWS actually provides less information about the image. GCP gives like the full set of classes, but AWS provides only recognized classes. And this is something that doesn't help you to to craft an adversarial example.
Yeah.
Yeah, but like here is something for AWS. Like let's do this bus. Yeah, and it's just a pillow. Yeah, but still you can recognize this as a bus. And we tried to use those images, and they have impact.
There is a question from the chat. They're asking if the attacks are optimizing the L-infinity perturbation or L2 perturbation.
In this case, it's L-infinity perturbation, but you can consider both.
Okay.
Yeah, so as you can see, we try to optimize like all pixels. So like whatever, we start with the easiest way to do this, and then see how it goes and decide on top of it. Yeah, so about this natural evolution strategy approach. The good thing is it actually works. So you see it. There is no restriction on target function. Like if you just, even if you don't have scores, you can just try to assume that if you have, for instance, 5 labels out of your model, that the score is like 1 divided by 5. And you just try to push your kind of class of interest, for instance, out of top K classes for prediction. And actually you can ensemble models. So like you can mix pre-trained model with vision API. You just use the population scores for both API and model and try to estimate the gradient. Basically, it totally makes sense because, you know, if there is a problem, for instance, in a certain budget to break ResNet, you can mix other models and maybe the result from other model would help you to recognize the right direction out of your example and craft kind of new adversarial example. Cons, basically the targeted scenario is quite hard. Because of this approach, if you want to go into a certain direction, you have to start keeping this label in your population. If you lose this label, you can't understand like what's the right direction. You can wait for several iterations and maybe it will occasionally appear like in the output and you start using this for gradient estimation, but it might not happen. And in order to actually fix this, usually like one of the image that has targeted label is mixed with the original image. So if you want to make a dog from a cat, you have to start like mixing a dog and the cat and then try to eliminate dog as much as possible, but keep dog like as your targeted class. And at the end, if you would look closely into this kind of adversarial image, it has like a light dog in background, which makes it like a bit tricky to use. And yeah, a lot of iteration per input. So you have to execute around 1,500 requests per image in order to craft an adversarial example, which is actually not bad because like if you want to attack Cloud Vision APIs, in most of them, 2,000 requests cost like $1 and this is not a big deal. But as I mentioned before, we have 100 million impressions per day and we are like instantly interested in attacking, let's say, 100,000 images from the very beginning. And the whole setup makes it like quite costly for us from that perspective. So how we try to optimize that, we actually try to reuse noise patterns. Like, let's say you pick like 100 images for attack and you start running the whole process, like crafting noise patterns for crafting dedicated noise patterns for every image. And when you get all those 100 patterns, you can just try to mix them randomly. By averaging, you can take 3, you can take 5, whatever it works. And what happens here, if we start mixing them, we actually detach them from images. So now, like our new pattern doesn't really connect with the image that like, because it wasn't originated by this image. And the next step, of course, like if we have patterns that are not connected with images, then we can just try to scale them. What if we, in this case, we make noise even less? So let's say we crafted like a set of adversarial images with the full cycle, and this is kind of our like original scale. And then we detach those noises from images and try to generate new patterns. And this is how, so like in the first case, we have 100% of our, like 100% success of our attack, because like each image is crafted specifically for the model. Then we just try to extract those noises and mix them. like for different models, our success rate drops like around 80%, which is still fine. It is possible to scale. The truth behind this process is that we know that some bots will pass. Even like just randomly picking images, they can be lucky and they will succeed in some cases. So we are fine with maybe 80% of success. If we go further, like if we try to scale 0.7, then we have like 60% of success. This is more or less fine, but of course we want more. And we can't go like, if we have, again, like 0.5 scale, then it drops dramatically. Kind of similar for most of the models except YOLO, which is not a surprise here. Most of YOLO models that are used across internet, they have input tensor of like around 608 and 608, maybe 400 size. And what happens is that if you try to ship our images, which is around like 120 pixels, they are heavily pixelated, and together with noise and together with first wide convolutions of YOLO, it makes them like totally unclear for the model. And this is why, like specifically for YOLO, it looks like this. For other models like ResNet, Inception, it is around like 225 or around it. And from that perspective, they are kind of better prepared for using small images in that case. Any questions so far?
We have a question from the Zoom chat, which is, did Google or any company detected the volume of queries and banned the account, or did you encounter some restriction from them?
No, because they sell their API. Basically, they want more. Like, do whatever you want. Yeah, you can craft adversarial examples. Maybe you need it, but just spend more money. And we haven't experienced something like that. And basically, for this specific case, I talk about it in like more in details because we don't use this in production. For the reason that I already mentioned, it is quite, I mean, we can scale this in this way, but noise is still visible, and we still have to allocate some budget for that, like constantly, to regenerate all those noise examples, because at some point, every adversarial attack, especially black box attacks, could kind of degrade quite fast, because like bots try to adapt and they can use denoising and stuff like that. And from that perspective, we didn't do like really a lot of requests, but I don't see this as a problem, yes, because they just want to get money from you, and if you do more, then they're just happy about it.
I have a question too, which is if basically your goal is to use adversarial example to make bot not able to correctly recognize the image, in which scenario you are interested into computing targeted attack? Because you talked about bot. It's maybe to create image that facilitate like you into understanding that there is a bot behind, because it classifies something like a specific class that is the one for which you computed the image, or there is another reason why you are interested also in targeted attack?
Yes, this is something that is called like a honeypot approach in cybersecurity. We can put something that actually like bot can recognize as a pillow, but this is actually a bus. And this is kind of a signal for us to do, to investigate further what's behind this source of traffic, let's say. But we are quite fine with untargeted attacks. And like most of my presentation is about untargeted attacks because they are easier to make. And as I mentioned, like bots will pass anyway. And there is something behind bots which is called a click farm, where people try to solve captcha, but like on as a job, let's say it like this. So they just sit and solve all captchas they see. What we try actually to do, we want to increase the budget, and we want to increase the time that bot needs to pass the gate. And we are totally like, this is why we try to evaluate different approaches. Sometimes we are like to find the right balance to make it good for human, like with less noise, but keeping some balance like with the attack success rate. And yeah, this is what it's all about. And we need a decent variation of images, because we can, like, I will tell about this later, because you can just increase the set of images also. But like, it is always a question how to scale. Like if you have 100 million impressions a day.
Sure. Thank you.
Okay. I will continue then. So this is about the first approach that we tried, like natural evolution strategy, which is successful but doesn't really satisfy our needs. And one of the other approach that seemed to us quite interesting was using GANs, after all. So here is a simple example, like how GANs can be applied for this field of adversarial attacks. Basically, you try to make a generator that can perturb like your image, and there is a part that try to serve this generator discriminator pattern, and there is another part that contributes to the like adversarial loss. And in this schema, which is taken from ADV-GAN paper, they say that basically like they use distilled black box scenario. So kind of they recommend to use distilled model to craft an adversarial example, but you can actually put an oracle here. So you can use API that contributes to like adversarial loss and craft your adversarial examples. It seems to be more complicated, but the an obvious advantage is that all like previous iterative approaches that can be easily described by some simple formulas and by some simple math, but they work actually longer, because once you craft a generator, you have only like forward pass to create adversarial example. So this is kind of like massive query optimization problem. If you need to execute several queries, then you can like spend more time to one single query. But if you need to execute a lot of queries, it makes sense to spend more budget in the very beginning, but then optimize the execution of those queries. And it's actually easier to create batches, of course. So you can like use CPU, GPU, you can optimize this process from various perspectives. unfortunately, like we use several variations of this approach, and this is why I don't want to go into many details here, like about it, because it is kind of in production. What I can say is that noise is still visible, just like in this example. So we can't solve this problem of having subtle perturbation, just like in a white box scenario. And of course, there is the question of pattern diversity. You never know how the process would be optimized in this case. So like kind of have a lot of queries, but just like with other GANs, like can be shifted towards some like better images. And when you go outside of different manifolds, you can just like have less variations of something that you actually want to achieve. At least this is from our perspective. So it's better from our perspective, from the perspective of scaling, but still not ideal for our scenario. And another attack that I want to mention briefly that we also tested, and it actually breaks the rule of thumb that when you have a gradient, it's better than not to have gradient for the black box attacks, is this square attack. What happened here is that there is some kind of random selection of points and special modification of areas around those points to craft those like boxes that try to hide information, which forms the adversarial attack in this case. I think that I haven't explored it myself, but I think there is a potential to change the pattern. Actually, there can be like circles or like whatever other patterns to achieve the kind of a case when you want to craft more different adversarial examples, but this is still iterative approach. So you still have to optimize it, like, I don't know, mixing patterns in order to scale it effectively. And it's better for like, again, untargeted attack and quite problematic for targeted attack. So like, if you're interested, you can explore it also a bit more in detail. But kind of this is all about the classical topic of targeted black box attacks in our case. Yeah, so any questions, opinions so far?
I don't see questions. Quick question. Do you have more slides or this is...
Yeah, I have more slides.
Okay.
Okay, let's continue then.
Yep.
So when we did those experiments, we finally tried to formulate like what we actually try to achieve and what's the goal behind it. Like, because we have something that works, of course it have like pros and cons, and what is the direction that we can like formulate and go in that direction to achieve like better results. And we said that like image perception is a key, as all images are public. Like if we show something weird or strange, like goes to Twitter. So actually, believe it or not, but people tweet about captchas. Ideally, it should be actually entertaining because many people consider captchas bad UX. So it's good to have like better perception about the product. Yes, I mentioned bots will pass anyway. So it's better to have less noise, but better looking images, and we actually want to have like higher transferability. So we don't want to craft like a lot of models for every specific case. So it's better to have something universal. And the surprising outcome was that we decided to just start doing classes that no pre-trained models can handle. Yeah, what is the best adversarial example? Something that you don't know at all. And we started generating, for instance, seaplanes. That was the first idea. As we originally had boats and airplanes, in our pool of challenges, we kind of thought that seaplanes is something in between, and we can mix it with boats and airplanes, and it would be hard to recognize after all. Yeah, the funny thing was that, like, what bots did in order to overcome this problem, they tried to understand what kind of like confidence threshold described like seaplanes in some cases, and they tried to introduce that. And after that, of course, they can train images and create their own dedicated model for seaplane. But yeah, but we can retire challenge at that time. But this was quite successful. It actually lived for 2 or 3 months in my memory. So when we started it, I think it was like a good idea to try. All those seaplanes, by the way, all of them are artificials that are generated. And this is how we like continue explore guns for our case. Yeah, and after that, we just unleashed our creativity. So like the first success was smiling dogs. These are GAN modified dogs, and people start talking about it. Then of course like some rabbits, and here you can see like some duck, which is kind of a mutant duck. Sometimes it happens, but still this is kind of acceptable, because it's like, if it's a problem for bots and people still recognize this as duck, this still works. In the end, we can do holiday specials right now. So with the blast of diffusion models and DALL-E and other, like, we actually test all pre-trained generative models that are available on the market, and yeah, and try to craft our models. So this is something that really helps to, like, this is actually something that fit our needs, except maybe variability, because still we need like more. And with this regard, here is my like all speculation about the topic from the practical side. Yeah, so there are white box attacks, which is kind of interesting from the theoretical perspective, but doesn't seem to be really applicable. Black box attacks that we tried, they actually visible. So like, it is hard to imagine a case when you craft a black box attack and it's invisible. And if you want to have something transferable, this is even more complex. So hiding information is still a good way. I mean, if you would remove scores or any additional information from the model output, it would be hard to craft a black box attack in that case. Yeah, and this is something that I start thinking about, like dealing with all those scenarios, is actually adversarial perturbation, like, you know, not a big threat in real world, but this is something more about like doing some kind of, so now we have a lot of autonomous agents that consume like information, and some of this information may come from another autonomous agent, and there is a chain of those autonomous agents, just like in this example. So we create artificial images for artificial bots, like to do something. Those bots can transfer this information to other bots. We don't know actually what happens like in between of this process. Or you can imagine like automatically generated news that are consumed by trading bots or whatever other agents. And if you do perturbation in this scenario, this is really hard to predict what the outcome would be at the end of this process. More like this. So I would say that when I learn mathematical modeling, we've been talking about like mostly three topics: approximation, stability, and what next? Yeah, I just forgot about it. But I think that this adversarial example topic is mostly the matter of stability. We need to investigate how stable are models like in the chain of operation if you don't know what to expect from like another agent that can provide information. Not exactly like, you know, breaking Tesla or stuff like that. And otherwise, if you want to hide your face, let's say from Facebook or other like face recognition program, I still believe that you can just put glasses or wear a mask or like do something really simple but strong rather than just introduce some kind of adversarial noise as a perturbation to your image. Yeah. And finally, we are still interested in this topic, and this is what we're looking at. You've potentially heard about CLIP, and this is an interesting model like to classify everything because it can operate like with a lot of concepts. And there was a funny discovery that you can actually put a sticker and full a clip. And there is also interesting discovery that with CLIP you can still use adversarial examples because obviously it uses gradient to optimize. And you can mix it together. Even like this blog post described the case like how many stickers you need to put to change like the pixel perturbation, or how many pixel perturbation you need to change the sticker. And like the model became more sophisticated, it also became more susceptible to like different types of attacks, which is, I find, really interesting. And also there was an interesting post about like GPT-3. So so far you still have to do some, you know, sophisticated text manipulation to do an attack. But in our case, we also have a question which can be used to fool some decision making about our challenge. And it could be also an interesting direction of attack. And the question here is like, what is the minimum thing we need to do to achieve misunderstanding between the text and the model? Yeah, and this is basically it. So I hope it was quite, how to say, different from other talks that you have in this group, but yeah, thanks for listening. And if you have any questions, please, I'm here to answer.
Thank you a lot for the talk. Let's see if there are questions. We give the precedence to who take the microphone, then to the chat.
I think we have a quite short time for questions, so maybe we have space for one or two at most. And I see one from the YouTube chat. Should I go ahead, Amra? I think.
Yes.
So Julian asked, can we use this to train, meaning the last thing you showed, no, actually the second from last, the generative models things. Can you use this to train generative models? Like putting generated images in a captcha and see if they're recognized like they should be by a human, so it gets better. So basically relabeling the images and
Yes,
using these labels for training further.
we actually test all those images before. Like we have a selection. So obviously we generate a lot of images and we have a selection process in order to skip something that is too bad. But I think it's a bit different. So it's not exactly about like adversarial topic. I mean, if you produce something that has a different label that nobody knows, you're already fine, and then you would just make it, and then you just try to select something that looks better than the other thing. Yeah, but selective process actually involves human in the loop, so it's not entirely a GAN model. And if you will explore this topic, like even new sophisticated GAN models don't essentially give the best result that you can expect. Like sometimes images still weird, I would say.
Okay. I think I don't see other questions right now.
I have one in the meanwhile that people think. And it is, I mean, you have showed that basically making the life of both hard with the adversarial example, it's difficult. And instead you have showed us that generating some kind of image which are not usual for data set, like a ghost on a bicycle, that's better. So I mean, in production, you have to create really a lot of images. I'm wondering how you choose, I mean, if there is a human taking care of like finding images that could be hard for both, or if you have a kind of like automatic procedure that you use to select the topic, like a ghost on a bicycle, something like this.
Now it's mixed. So we
can't
automate everything, but obviously we use some lists and we use topics just like animals. So we figure out that people like animals, but this is also sensitive topics. Sometimes they like, sometimes they don't like it, like how we present them. And this is quite challenging. So it's still kind of experimental. I would say we are quite early about it after all, but like it's mixed at the end. Just like everything, I would say actually that just like everything like about machine learning production, it's mixed from some perspective today.
Thank you.
So I think we are ready to close even, I mean, also because it's 4:05. So we we should close the seminar, but thank you again, Andrei, because this was very interesting and different, as you said, from what we usually see, especially because you bring in the industrial perspective into our series that is always good to keep in mind when doing research.
Cool. I'm glad that I achieved that.
Yes, thank you a lot. And thank you all for joining, and see you next time. Bye-bye.
Thanks for the invitation. Bye.
Thank you for accepting.